Hello, welcome to Equity Education, the chemistry version. Alright, and today we're going to be looking at structure and bonding. Okay, so I'd like you to open up your booklets and we will get started. Okay, so structure and bonding. So structures. There are 4 distinct types of structures and you need to know these. Be able to describe the structure, be able to describe the bonding and the properties within the structures. So the first one that you need to know is a giant metallic structure. Our second one is a giant covalent structure. Our third one is giant Ionic lattice, and our last one is a simple molecular structure. It's going to write in brackets as well. You may also see this called simple covalence. It means the same thing. Okay, so these are our 4 different types of structures and we're going to go into a bit more detail with them. Right, so before we do that, they each have, so we're talking about the structures here, different properties. And a structure can generally be identified identified from its physical properties. So when we say physical properties, we mean a high melting point or a low melting point, things like that. Okay, so a giant metallic structure. So you may be asked to draw a labeled diagram of this. So you can have a go at drawing it. Doesn't have to be a work of art. Try and do it 3 by 3. Whoops. Right, so here's my diagram. I'm going to put some things in the middle. Okay, so this is my structure. Now we need to label it. So these positive things, these are our positive metal ions. And in the middle and surrounding them, these things, these are a sea of delocalized electrons. I'm going to define some words. Okay, so this word delocalized, and we'll include electrons in it. So delocalized electrons, what does it mean? Well, it means that the electron is not attached to a specific atom. And another way of saying that is the electron is free to move. Throughout the structure. Okay, and this is important when we come on to the different properties of a metal. Okay, so this is my giant metallic structure. An example of a giant metallic structure may be, for example, if we had, let's do it in green. So calcium. Calcium is an example of a metal. And if we follow this diagram, we need to form the positive metal ions. So calcium is in group 2, so this would be my positive metal ions. And I've lost these 2 electrons. So that means that this is my positive metal ion. And these are my delocalized electrons. Now this is a bit simplified, but it's just to get the idea of this type of structure. So you may have to be able to draw this, yeah, and you must label it. Okay, so my definition of metallic bonding is, so an electrostatic force of attraction between positive metal ions, basically just describing the diagram that I have just drawn, surrounded by a sea of delocalized electrons. Okay. Right, okay. Some examples of giant metallic structures. Well, I'll let you think of some of these, alright? I'll give you a couple of seconds to have a go at writing some down. Okay. Alright, I'm sure you've managed to figure this out. It wasn't a trick question. So, for example, we may have iron is an example of a metallic structure, magnesium, Mg, titanium. So any metal that it's on its own is going to be a giant metallic structure. Stands to reason. Okay, so moving on. Properties of metals. So they generally have a high melting point, and the way we describe this, or the way you need to describe it, is to use descriptive words, usually strong or weak. So if there's a high melting point, there must be a strong electrostatic force of attraction between positive metal ions and sea of delocalized electrons that require large amounts of energy to overcome. So I've described it by basically stating the definition and putting strong in front of it, and then stating that it requires large amounts of energy to overcome. Not very difficult. Okay, they conduct electricity, either solid or molten, and the reason why they conduct electricity is because the delocalized electrons, oops, I haven't left enough space, can flow through the metallic structure. Alright, because we have these delocalized electrons, they can move throughout the structure. And when we're talking about electricity, the electricity is the flow of electrons. So some electrons come into the structure and knock some of the delocalized electrons out the other end. Therefore, we have a continual flow of electrons, so it can conduct electricity. Okay. In general, well, not in general, so metals are insoluble, and that's because, I'm not going to go into too much detail here, no or little interaction with polar water molecules. So it can't really form any bonds or interactions with the water molecules, so it stays as this metallic structure because it has this electrostatic force of attraction between the positive metal ions and the sea of delocalized electrons. Okay, so if I drop some iron into, well, I won't say iron, let's do something which is non-reactive, some platinum into water, it's going to stay as a solid, it's not going to dissolve. But if you've done your group 2, then you'll know this, that they do react with water. So if I have magnesium solid, let me put it into some water. Now this is quite a slow reaction, but we still do get this reaction, plus H2. Balance it up. So this magnesium, when it's placed in water, does dissolve. It looks like it's dissolving because we're forming an aqueous solution and a gas, but what actually is happening is that it's reacting. Yeah, so it's still not soluble. We've gone from magnesium as a solid, as a metallic element, to magnesium hydroxide. So we've made something completely different. Okay, moving on. So it's got a hard, high tensile strength, and that's because, now I'm just going to use my definition again, and I'm going to stick strong in front of it. So strong electrostatic force of attraction between positive metal ions and a sea of delocalized electrons. Okay, so let's have a look at this question then. So why does magnesium have a higher melting point than sodium? Okay, so I'd like you to have a go at either filling it in or just thinking about it for about 30 seconds. I'll give you a clue. It's to do with the structure. Okay, so the force of attraction between the positive metal ions and the delocalized electrons. There must be something different because they've got different melting points and boiling points. Okay, so let's have a look at this then. So why does magnesium have a higher melting point than sodium? Well, we can say that magnesium has a greater charge or higher charge on the metal ion, since it's 2+, a smaller cation radius, therefore it has a greater charge density. I'll explain this phrase in a minute. There are two delocalized electrons, so that should be electrons per metal cation. Right, so that means there is a strong electrostatic force of attraction between positive metal ions and CO delocalized electrons. Therefore, it requires more energy to overcome these forces of attraction when we compare it to sodium. Okay, so we've got 3 different points here. We've got that the metal ion has a greater charge, the cation, so the metal ion is also smaller, and we've also got more delocalized electrons per metal cation. Okay, so but I use this phrase, charge density. So charge density means the charge on an ion, because we're talking about iron, so I should really put charge density of an ion, given its volume. E.g., so if I have Mg2+, so I'm going to take my Mg2+, and say it has this radius, and it has a charge of 2+. Sodium, the cation, is bigger. I'm exaggerating here. And it has a smaller charge. So we have a smaller charge and a bigger volume. That means that sodium has a lower charge density. Less charge in a bigger volume. Which means that magnesium has a higher charge density because it has more charge, 2+, in a smaller volume. Okay, I hope that clears that up. Okay, moving on. So, move on to giant covalent structures. Okay, so giant covalent structures. Some examples of giant covalent structure are, and I'm sure you know this already, are diamond, graphite, and we'll put in silicon dioxide since that's the other most common one. Silicon dioxide, which is SiO2. Okay, so now we're talking about giant covalent structures. You need to know what type of bonding is in giant covalent structures, and unsurprisingly, there's covalent bonds. Okay, so your covalent bond definition is the strong electrostatic force of attraction between a shared pair of electrons and the nuclei of bonded atoms. So it used to be just a shared pair of electrons, but they've updated it now. You might get away with just saying a shared pair of electrons, but we'll stick the definition they seem to like down now. Okay, so moving on to the types of properties for giant covalent structures. They have high melting points, and that's because they have strong covalent bonds between each atom that require large amounts of energy to break. Therefore, they have a high melting point. Okay, they do not conduct electricity when they are solid or molten, and that's because there are no delocalized electrons. Again, I haven't left you enough space, so right down here. Or mobile ions to carry the charge. Okay, so we talked about why delocalized electrons structures with delocalized electrons can conduct electricity. I haven't mentioned these mobile ions. We'll talk about that next, okay? Okay, and insoluble because there are no or little interaction with polar water molecules. Now I've used this word polar again, so if you don't know the word polar, then I suggest you watch the video on intermolecular forces, and that should start to clear up what this word polar means. Okay, they are hard because they have strong covalent bonds between each atom. Okay, pretty straightforward. Right, so these are our two very common examples of giant covalent structure, diamonds and graphite. Okay, so diamond has the structure. There are 4 strong covalent bonds between each carbon atom, and then we'll just add a little bit more to this, arranged in a tetrahedral shape. Again, if you don't know what this word tetrahedral is, I suggest you watch the video on shapes of molecules, but it basically means that we have, if we go up here, this is my carbon atom, 4 strong covalent bonds. Yep, these lines represent the covalent bonds, and they have this tetrahedral arrangement. This is a tetrahedral arrangement. And giant, which I should have mentioned earlier, giant, what does giant mean? Giant means that there are lots of particles put together. Okay, so there might be millions of them. We don't know the exact number. Okay, so that's what we mean by giant in terms of structure when we're doing chemistry. Okay, so going back down, properties and use of diamond relating to its structure. Right, it's hard. Well, why is it hard? Well, it's because it's got 4 strong covalent bonds between each carbon atom. So we can write that down again. So 4 strong covalent bonds. And what's it used for? It's used for drilling. I'll write that in a different colour. So it's used for drill bits. So to cut things. So cutting. Diamond is also shiny, and that's because of the regular arrangement of the carbon atoms. And because it's shiny and because it's pretty rare, we use it to make jewelry. Okay, moving on. So graphite structure. How do we describe graphite? Well, graphite has hexagonal layers with strong forces, with weak London forces between them. And there are 3 strong covalent bonds. They shouldn't be capitalized. I'm just going to change that since I've noticed it now. Bonds between each carbon atom, and each carbon atom has 1 delocalized electron. Again, I haven't left you enough space, allowing it, or the structure, to conduct electricity. Okay, so we'll read through it, then we'll look at the diagram at the top. So they're hexagonal layers with weak London forces between them. 3 strong covalent bonds between each carbon atom. Each carbon atom has 1 delocalized electron, allowing it to conduct electricity. Okay, so if we go back up, here's my example. Yep, so there's the hexagonal layers, 1, 2, 3. There are 3 strong covalent bonds between each carbon atom. Now, because there's only 3 covalent bonds, it means that each carbon atom has 1 delocalized electron. So if it has one delocalized electron, it means that this structure conducts electricity. And on this, we're just going to draw our London forces. So we have these weak forces between the layers, right? So we still have some force of attraction between the layers, so it means it's held together, but they are weak. So we call these weak London forces. Again, if you're not sure about this word London forces, have a look at my video on intermolecular forces. Okay. So, properties and uses of graphite related to structure. Right, conducts electricity. Well, we know it conducts electricity because of the delocalized electrons. Can flow through the structure. And we use it for making electrodes, which I'm sure you've seen before, or maybe even used them when you've been doing an electrolysis experiment in the lab. Also slippery. Why are they slippery? Well, if we go back up to look at this diagram, we've got these weak forces between the layers, right? So if we've got weak forces between the layers, it means they're easy to break. So the weak London forces are easy to overcome. Therefore, they can slide off each other. And because they're easy to overcome, it makes them slippy. So every time if you rub on some graphite, you'll feel slippy, and that's because you're pulling layers off it. Okay, and its use is that you may see graphite used in pencils. So your pencil is probably made of graphite. You will also, or you may know that it's used as a lubricant as well. Okay, so moving on. So a giant ionic lattice. Right, so what is a giant ionic lattice? Right, so ionic bonding, again, going up to here, giant. So it means that lots and lots of these ions are in a regular arrangement, but there's millions of them. We don't know how many there is, hence the word giant. Okay, so my definition for ionic bonding. So ionic bonding is the strong electrostatic force of attraction between oppositely charged ions. And if I go up here, I can see this. So here's an example of a giant ionic lattice. This is my chloride ion, this is my sodium ion, and it shows that there's a regular arrangement of these oppositely charged ions. Okay, so we know that our formula for sodium chloride is NaCl. Now this is important. So what this actually shows is something called a formula unit. Now a formula unit tells me the ratio of oppositely charged ions in the compound. So NaCl tells me that for every one Na plus ion, there is one chloride ion. Okay, it doesn't tell me that a giant ionic structure contains one Na plus ion and Cl minus ion. It only tells me the ratio of them. Remember when we're talking about giant, there might be millions of these different ions, these oppositely charged ions in a structure. Okay, so here's we'll just do some quick examples. So we've got NaCl. Another example might be MgCl2. And we'll do one more. What shall we do? CaBr2. So these are all examples of ionic structures. Remember that ionic bonding occurs between a metal, such as sodium, and a non-metal. Okay, so moving on to the properties, they have a high melting point. But you can't guess why, because there is a strong electrostatic force of attraction between oppositely charged ions. Again, I'm just using my definition, sticking the word strong in front of it. Well, actually, I've done that in the definition up here. That requires a large amount of energy to break. Moving on, soluble. Okay, usually. So they're usually soluble. And this is because the charged ions can interact with the polar water molecules. I'll go into a bit more detail with this then. Okay, so I'm going to draw a diagram. So this is my water molecule. I'm not going to go into too much detail, but a little bit more. Okay, so I've got a water molecule. I call this polar, and the reason why this is polar is because oxygen is more electronegative than hydrogen. So the electrons move towards the oxygen, so it becomes slightly positive. That's what this delta negative means. And this is delta positive, so the hydrogen becomes slightly positive. Slightly positive, slightly negative. That's what polar is. Again, if you want to know more about this, watch my video on intermolecular forces. Okay. Now I have some charged ions as well, so I have Na+, and I also have Cl-. Now, we have, between my negative here and my positive, a force of attraction. Between my positive here and Cl-, we have a force of attraction. And because there is a force of attraction between these, between my charged ions and the water molecules, it means that the ionic compound in question will dissolve in water. Okay, again, quite a simplified explanation, but that will do for now. Okay, moving on. So they also form crystal-like structures, and that is because of the regular and uniform arrangement of ions in the structure. Again, I'll just show you what I mean. So I'll go up and here. So this is a regular and uniform arrangement. Positive, negative, positive, negative, positive, negative, and so on and so on and so on. Okay. So they do not conduct electricity when solid. So why don't they conduct electricity when solid? This is because the ions are fixed in position. There are no mobile ions to carry the charge. So ions can carry a charge, or the electricity, the electrons, through a structure, but to be able to do that they have to be able to move. If they're in solid, they are in the solid state, then the ions are fixed in position, between the strong electrostatic forces of attraction. Therefore they can't move, so electricity cannot be conducted. However, they do conduct electricity when molten or dissolved in water, and that's because the ions are free to move. There are mobile ions that can carry the charge. Right, I'll just explain this a bit. So I put the ions are free to move and they are mobile ions. Basically means the same thing. However, in some syllabuses they don't like you to use the word mobile ions, so I've included two different phrases, so you'll always be sure that you get the marks. Okay, so moving on to our last type of structure, we have a simple molecular structure. Right, so some examples of simple molecular structure. Actually, you can do this, so see if you can think of some simple molecular structures. Okay, so some simple molecular structures, e.g. carbon dioxide, water, methane, ammonia, and lots more, and we'll do one more. HCl, hydrogen chloride. Okay, so simple molecular structure. Okay, so what is a simple molecular structure? So it is a fixed number of atoms that are chemically bonded together. E.g., carbon dioxide has one carbon atom and two oxygen atoms bonded together. Now it has to stay as one carbon and two oxygens, yeah? If we change the number of carbons and oxygens, we would change the molecule completely. Hence why our definition is a fixed number of atoms that are chemically bonded together. Okay, moving on to the properties. So they have low melting points. Okay, so all simple molecular structures have low melting points compared to other types of structures, and that's because they have weak intermolecular forces between molecules. Okay, I'll talk about intermolecular forces in a minute. Okay, they do not conduct electricity when molten or solid because there are no delocalized electrons or ions to carry the charge. Be a bit more specific, you'll get away with just saying ions, and I would say mobile ions to carry the charge. Obviously it's a covalent molecule, therefore it doesn't have any ions, it's not ionic, and there are no delocalized electrons because our only exception, we're talking about covalent compounds that you need to know, is graphite that has these delocalized electrons. And that also is a giant covalent structure. Okay, so write out the equation including state symbols for an iodine gas goes from a solid to a gas. Well, let's read it right. So write out the equation including state symbols for an iodine goes from a solid to a gas. This is called sublimation. Okay, I want you to have a go at doing this. It's not a trick question. Okay, so lots of students seem to get confused by this, but it's not particularly difficult. So we know that iodine is I2. As a solid, if I write the state symbol, it's S. As a gas, it's also going to be I2. So all we have done is change the states. Okay, so why have I got you to do this? Well, it's because if we think about the structure of our iodine molecule here. So I have a molecule of iodine. I'm not going to draw it 3D, I'm just going to draw it like here. Now, as a solid of iodine, we know that that must be a force of attraction between my iodine molecules. Because otherwise, if there wasn't, it couldn't be a solid. It would just be a gas. So we have this force of attraction. So this is a force of attraction between my molecules of iodine, which means that it's a solid. It's also a regular crystal-like arrangement. Okay, so when I heat this, what happens to this force of attraction? Well, as we get more heat, these iodine molecules start to vibrate more, they overcome this force of attraction, and they end up as iodine gas, where they're just floating around randomly. Okay, so all we have done when we're going from a solid to a gas is to break these intermolecular forces of attraction. Okay, that takes us on intermolecular forces. So intermolecular forces, which we have been using, our definition is the forces of attraction between molecules. So this is my force of attraction between the molecules, so this is an intermolecular force. Okay, if I now look at one molecule, I'm going to have to do it up here, of iodine. I know that iodine, if I did the dot and cross diagram. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 would look like this, which means that here I could also draw it as this, and in the molecule of iodine is a strong covalent bond. Now we know that covalent bonds take lots and lots of energy to overcome. So it's not this force of attraction, this covalent bond, that we are breaking when we are changing state. We are only breaking the weak intermolecular forces when we change state for a simple molecular structure. That's why they have low melting points. Okay, so again, moving on, so intermolecular forces play a big role in determining the melting point of a simple molecular structure. There are 3 different types of intermolecular force, and I will name them now, but there's a whole new video or another video on intermolecular forces which I suggest you watch. Okay, so our 3 different types of intermolecular forces are London forces, permanent dipole to dipole interactions, and hydrogen bonding. And again, as I said, there's another video, but we will just do this now. And the strength of intermolecular force. Okay, so my weakest intermolecular force is London forces, and my strongest is hydrogen bonding. Okay, that's all I want to say about intermolecular forces for now. Okay, so your turn. Okay, so there's a couple of questions that I'd like you to have a go at, and we'll go through them. There's 1, 2, 3 questions. There's a fair amount of work to do, so I reckon this might take you 20 to 30 minutes. So have a go at doing this, and then we will go through it together. Okay. Okay, so I'll go through this table which I asked you to fill out. Pretty straightforward. Gave you an example, talk about the structure and bonding and the properties. So, iron is a giant metallic structure, has metallic bonding, has a high melting point, it's insoluble and has a high electrical conductivity when solid and when molten. Silicon dioxide is a giant covalent structure, has covalent bonds, it's got a very high melting point, it's insoluble and has no electrical conductivity or no electrical conductivity. I've put low, but really it's none. Or none. No. Giant ionic lattice, ionic bonding, high, soluble, again, low or none when solid. When molten, or dissolved in aqueous solution, it's high. CO2, it's a simple molecular structure. It has covalent bonds between the atoms, remember? However, between the molecules, it has intermolecular forces. And that means, because it has weak intermolecular forces between the molecules, it has a low melting and boiling point. Now, solubility. But it varies for each molecule. So carbon dioxide is soluble in water, okay? I don't really want to go into too much detail about this at the minute, so have a look at the intermolecular forces videos, because I'm going to be using words that you may not have heard about before. It's got low or none or no electrical conductivity when solid, and low or non-electrical conductivity when molten or dissolved in an aqueous solution. Okay, so moving on. So we'll go through this a bit more slowly. We'll write it down. So aluminium has a high melting point of 660 degrees Celsius, and magnesium has a melting point of 650 degrees Celsius. So they're both high. Explain why they have similar melting points, but why aluminium's is higher. Well, we can say they have similar high melting points, and that's because there is a strong electrostatic force of attraction between positive metal ions. And sea of delocalized electrons. So that explains why they both have high melting points. Again, I've just used my definition and I stuck the word strong in front of it. Okay, but we have to describe why aluminium has a higher melting point than magnesium. Okay, well, aluminium, Al, has a higher or greater charge compared to magnesium. So it's Al3+. It also has a smaller cation radius, and therefore this word we used previously in our examples above, therefore a greater charge density. We also know that there are 3 delocalized electrons per metal ion. Therefore, stronger forces of attraction in aluminium compared to magnesium. Okay, so if you're unsure about this, if you go back up, you will see this example for magnesium and sodium. It's exactly the same thing, however we're using aluminium and magnesium in this example. Okay, so for the following descriptions, state the structure and the bonding within the structure for each description. And let's say that again. For the following descriptions, state the structure and the bonding within the structure and the bonding within the structure for each description, and explain your answers. Okay, so compound A has a high melting point, so we know it's not simple molecular. When dissolved in water, it conducts electricity. Okay, so I should have really said when it is a solid, it does not conduct electricity. I reckon you've probably figured this out yourself though, so we'll go through the answer. So the structure is, so we know that it conducts electricity when it's dissolved in water, but not when a solid, and it has a high melting point. Therefore, it must be a giant ionic lattice, which means the bonding is ionic bonding. And my reasoning, so I have to explain these different properties. So it's got a high melting point. It's got a high melting point because of the strong electrostatic forces of attraction between my oppositely charged ions. And I also have to describe that it conducts electricity when molten or dissolved in water but not solid. So it conducts electricity when dissolved in water but not solid. So I would say that as a solid, there are no mobile ions, or the ions are fixed in position. The ions are fixed in position. When dissolved, the ions are free to move. And can carry the charge. will conduct electricity. Okay, moving on. So, compound B is a black solid that does not melt at 1000 degrees Celsius, hence a high melting point. It will not dissolve in water but will conduct electricity as a solid. And another property, it is slippery to touch. Right, wow. This one's a bit of a tricky one. Yeah, it's a black solid. Okay, got a high melting point. So it could be giant covalent, giant ionic, or giant metallic. It will not dissolve in water but will conduct electricity as a solid. Well, that sounds like a giant metallic. However, it is slippery to the touch. Metals aren't slippery to the touch. So this is a bit of a curveball one. I'm going to say that this is a giant covalent structure. And you may be thinking, wow, how can it conduct electricity as a solid? And that's because it's a specific substance and it's graphite. So that means I have covalent bonding, and I need to describe these properties. So how do I describe these properties? It's a black solid with a high melting point. Right, so it's a high melting point because it has 3 strong covalent bonds. Carbon atom. That requires lots of energy to overcome or break. It conducts electricity as a solid. Okay, so it conducts electricity, and that's because there are delocalized electrons that can flow through the structure. And what else we got? It's slippery. And it's slippery because there are weak intermolecular forces between each layer. Weak London forces, not intermolecular, don't like that word. That are easy to break so the layers can slide over each other. I feel like I've done a lot of writing in this one. Okay, last. Okay, my hand's hurting. So compound C is a gas at room temperature at a melting point of minus 98 degrees Celsius. As a solid, it does not conduct electricity. Right, so the only one of our structures that has a really low melting point is simple molecular. So it must have a simple molecular structure. Its bonding is covalent. Remember, we're talking about in the molecule. However, when we talk about the reasoning, it's got a low melting point. Well, it has a low melting point because it has weak intermolecular forces between molecules. That require little energy to overcome. Okay, and what's our other property? As a solid, it does not conduct electricity. Well, it's a covalent structure, which means that there are no delocalized electrons. Or ions to carry the charge. Okay, And we are finished. Right, so I hope that was useful. Right, there was quite a lot of information. However, if you just remember this and then apply the different properties to the different types of structure, you should be able to answer all of these different types of questions. You need to commit it to memory though, okay? So go away and learn it. Make sure you know the definitions, make sure you know the properties, and as I said, I hope that was useful. I'm going to go and have a rest because I've done too much writing, and I will see you next time. Okay, bye bye.